You've probably wondered how the biggest websites on the planet don't just crash during huge events. Well, it's definitely not luck. It's all about design. Today, we're going to break down the 7 core concepts that make these systems so incredibly reliable.
So, let's just jump right in with a big question. How on earth does a site like Amazon survive the absolute madness of a Black Friday traffic spike without just completely falling over? Or think about this. How do banking systems make sure your money is safe even when the network is acting up? It's not magic. It's all about a very specific kind of engineering.
And that right there gets to the absolute heart of it. You see, the big secret isn't trying to build a system that never fails, because let's be real, that's impossible. The real goal is to build a system that expects to fail. It anticipates problems and has a plan ready to go when they inevitably pop up. All right, so where do we even begin? Well, we start with what feels like an impossible choice. It's this fundamental trade-off that every single person designing a large-scale system has to face. And this big choice is all wrapped up in something called the CAP theorem. Think of it as like a fundamental law of physics for distributed systems. It says you get a menu of 3 guarantees. You've got consistency, which means everyone sees the exact same most up-to-date data. Then there's availability, which just means the system always answers your request. And finally, partition tolerance, which means the system keeps chugging along even if different parts of it get disconnected. Now here's the kicker. You can only have 2. Okay, but here's where it gets really interesting. In the real world, networks fail. It's just a fact of life. So that P for partition tolerance, it's not really a choice you get to make. It's something you have to have. So the game really boils down to one crucial decision. Do you prioritize consistency, being 100% correct all the time? Or do you prioritize availability, being open for business no matter what, even if the data's a little stale? And you see this choice play out everywhere. Take something like Google Spanner, which powers a lot of financial services. For them, consistency is non-negotiable. I mean, you'd rather the bank's website be down for a minute than show you the wrong account balance, right? But then you have Amazon's shopping platform. For them, availability is king. They would much rather you be able to add something to your cart, even if the stock count is a few seconds out of date, than tell you, sorry, we're closed.
Okay, so you've made that big, critical choice between being always right or always on. Now what? How do you actually make that happen? Well, that leads us right into our next set of concepts, all about data. So for those systems that picked availability, like Amazon, they often use a model called eventual consistency. It's basically a promise. The system says, look, some of our servers might have slightly different info right this second, but I promise, give it a little time and they'll all get on the same page. And that's why it feels so fast. When you add something to your cart, it confirms it instantly because it's not waiting for every single server across the globe to give it the thumbs up. But of course, that speed and growth creates a whole new problem. As your service gets more popular, you have to add more servers. So how do you do that without breaking everything? How do you add capacity without a massive, painful reshuffling of all your data that brings the whole site to a screeching halt? Well, the old school way was to use a really simple hashing formula to decide which server holds which data. But here's the huge problem. Imagine you have 10 servers and you add just one more, an 11th. That simple formula completely breaks. You'd have to remap and physically move almost all of your data. For a company the size of Netflix or Amazon, that's an absolute non-starter. The solution is this really beautiful, elegant idea called consistent hashing. The way it works is, you imagine all your servers are placed on a circle, like numbers on a clock. Then you take your piece of data, figure out its spot on the circle, and just walk clockwise until you hit a server. That's where it lives. But here's the real magic. When you add a new server, you just drop it onto the ring, and it only affects the data that falls between it and its next-door neighbor. You only move a tiny, tiny fraction of the data, not the whole shebang. It's brilliant. Okay, so we've got a really smart way to store our data and scale it up. That's awesome. But what about the traffic? What about that massive, unpredictable flood of requests coming from all of us, the users? How do you tame that beast? Your first line of defense is always going to be a load balancer. The name says it all, right? The simplest way to think of it is as a traffic cop for your website. Now, you've got 2 main types. The layer 4 guy is fast, but kind of simple. He just looks at basic info like IP address and sends you on your way. The layer 7 cop is much smarter. She can actually peek inside your request, look at the URL you're trying to visit, and make a much more intelligent decision about which server is best to handle it. A little slower, but way smarter. But what happens when one of the services that Traffic Cop is sending people to starts to struggle? In today's complex systems, one single slow service can cause a traffic jam. Requests start piling up, resources get eaten up, and then boom, you get a chain reaction, like dominoes falling, that can bring the entire system crashing down. It's called a cascading failure, and it's a nightmare scenario.
So the big question is, how do you stop that first domino from falling, or at least stop it from knocking over all the others? This is where a brilliant pattern, pioneered by Netflix, comes into play. It's called the circuit breaker. And yeah, it works almost exactly like the circuit breaker in your house. When it detects a dangerous overload, it trips and cuts the connection.
It has 3 simple states. Most of the time, it's closed and traffic is flowing just fine. But if it starts seeing too many errors from a service, bam, it trips and flips to the open state. Now, all requests to that struggling service are immediately stopped. This is crucial. It gives that service some breathing room to recover. Then, after a little while, the circuit moves to half open. It cautiously lets 1 or 2 requests through, just to test the waters. If they succeed, great, the circuit closes and we're back to normal. And this really gets to the core philosophy here. A fast failure is always better than a slow one. It's much better to tell a user, sorry, something went wrong, please try again in a moment, than to let their request just hang in limbo, eating up precious resources and pushing the whole system closer to a meltdown. Another huge piece of the puzzle is rate limiting, and the best analogy for this is a bouncer at a popular club. Their job is to make sure the club doesn't get dangerously overcrowded. Rate limiting does the same thing for requests. There are a bunch of ways to do it, but a common one is the token bucket algorithm. Basically, you give every user a bucket with a certain number of request tokens. Every time they make a request, they spend a token. If their bucket is empty, they have to wait for it to refill. It's a super effective way to stop one person from hogging all the resources. Okay, so at this point, we've got a system that can scale its data, handle failures, manage a flood of traffic. But how do we know if it's actually working well? How do we know it's healthy? I mean, with all this complexity, are we just flying blind? How do we see through all the noise? Well, it really all boils down to that timeless engineering principle. You just can't manage what you can't measure. Period. If you want a reliable system, you absolutely have to know what's going on under the hood. And this is where the idea of observability comes in. It's about piecing together a full picture of your system's health from 4 key signals. You've got metrics, that's the what. What's the CPU usage? What are the response times? Then you have logs, that's the why. A detailed story of a specific thing that happened. Traces give you the where. They're like a GPS for a single request, following its journey through all the different services it has to talk to. And finally, events tell you when. When did we deploy new code? When did a server restart? You put them all together, and you finally have a clear picture of what's going on. But here's the thing. Just collecting mountains of data isn't the goal. The real point is to use all that info to answer one question. Is the user having a good experience? Are pages loading fast enough? Are people able to buy the thing they want to buy? All those technical signals have to translate into real-world human impact. That's the only thing that really matters. So let's pull all this together. We've talked about a lot of different concepts and tools, but really, they all serve one single golden rule for anyone designing these kinds of systems. And that rule is simple. Everything is a trade-off. There is no single perfect answer. It's always a balancing act. So I'll leave you with this. The next time you're scrolling through an app on your phone, just stop and think for a second. Is that social media feed prioritizing availability by showing you a slightly older post just to be fast? Is your banking app prioritizing consistency by making you wait that extra half second for a transaction to go through? These choices, these trade-offs, are being made constantly in all the invisible architecture that powers our digital lives.